Okay, and afterward to share the screen. Okay. So is everything okay? You can hear me, you can see the screen.
Yes, we can.
I see some yes. So everything is clear, it seems. Oh, okay. The first exercise was very easy. It is quite different for everybody of you because the coefficient alpha basically distinguish between the different students, and the coefficient alpha is related to the first letter of your first name. Okay. Afterwards, the second exercise was related to a cross-section in steel 235, which is characterized by a yielding strength of 235 Newton per square millimeter, and there are several things to compute, starting with the moment of first yielding, to the fully plastic moment, to the terms WL and WP, and to the plastic ratio psi. The plastic ratio psi, as you remember, might be defined as the ratio between MPL and MY, or alternatively, the ratio between WPL and WL. I've seen from the answers in the chat that many of you have had some difficulty on this second exercise. Again, this exercise is different from everybody because the width of the flanges are different in terms of this coefficient alpha. Okay, so let's move to the first exercise. I will show the solution for a certain value of alpha, in order that we have that this value of the load is QL over 2, and this value is 1.5 L times 2. Okay, this is a classic arch with 3 hinges. So there are in this classical scheme 2 beams which are connected between themselves and with the ground by using 3 hinges. In this case, the peculiar aspect is related on the fact that we have basically 4 unknowns which are corresponding to the external reactions. So, in order to evaluate these 4 unknowns, we need basically 4 equations. The first 3 equations are coming from overall equilibrium of the 2 beams as a rigid body, okay? So are coming from the statics of a rigid body. But the ensemble constituted by the 2 beams is not indeed a rigid body. Why it is not a rigid body? Because we have an inner hinge, and the inner hinge in principle might allow a relative rotation between beam AB and beam BC. Sorry. So what we have to do in order to obtain the last and fourth equation of equilibrium is to state that there is no relative rotation, for example, between beam BC and beam AB with respect to point B. Okay? Since in point B there is an internal hinge, this means that the bending moment resultant on beam BC should be equal to 0. Okay, so in order to evaluate the unknown reaction, first of all, we can do a moment of resultant with respect to point A of the entire structure, because if we do this, the two external reactions in A are not part of this equilibrium equation. Also, the force I have called H2 is not part of this equilibrium equation, so the only unknown in this equilibrium equation is V2. And so I can easily evaluate V2, and the value of V2 is equal to 11/6 times QL. Afterwards, once I know the vertical force, the vertical reaction V2, the only vertical reaction which remains unknown is V1. And so it is very easy to write the equilibrium to the vertical forces in order to say that the vertical resultant on the overall structure is equal to 0. By doing this, we can obtain the value of V1, because V1 will be equal to the resultant of these uniformly distributed forces minus the value of V2, and the resultant value is 7/6 times QL. Okay, at this moment, the only unknown are the horizontal forces. Okay, so what we have to do, for example, is to evaluate the horizontal force H2 by making a partial moment of equilibrium on all the forces acting on beam BC with respect to point B. Okay, by doing this, the only unknown is H2, and very easily I can evaluate the value of H2 as 39/24 times QL. At this point, of course, the only remaining unknown is H1, and I can obtain H1 by applying the horizontal equilibrium of the entire structure. And so I can evaluate H1, and the value of H1 is 27/24 times QL. Okay, at this point, having evaluated the external reaction, it is very easy to evaluate the diagram of axial force and the diagram of shear force. So, first of all, let's see what happens in terms of axial forces. Okay, the positive convention for axial forces is the one with axial forces in tension. So let's look, for example, to this vertical column. We do not have any distributed forces along the axis of the column. So what I expect is that the axial force in this case is constant, and so it will be constant and equal to the value of the external reaction. The external reaction is in compression, and so minus 7/6 times QL for the column which is placed on our left-hand side. Let's look at our right-hand side. Again, no axial forces distributed along the column, and so again what I expect is that the axial force is again in compression because it's equal to the external reaction, and its value is equal to 11/6. So you can see very easily that if we want, we can write the evolution in terms of x of axial force and shear and bending moment. But generally, what is needed is just to compute the value at the extreme ends of our beam. If we are dealing with a beam without any axial forces applied along the length of the beam, we know that the axial force is constant. So we need just to evaluate just one value. For the upper horizontal beam, again, in this case, we have vertical forces, but not horizontal forces applied along the length of the beam. So also in this case, we can expect a constant value of the axial force, and it will be again in compression and equal to this value of this reaction, because if we make an ideal section in an ideal cut in any point of this beam, we can obtain exactly an axial force which is equal and opposite to this external reaction of 27 over 24 times QL. Okay, let's move to shear. For shear, we have similar aspects related to the columns, because we can see that in the two columns there are no forces applied orthogonally to the length of the column. And so what we have to expect is that the shear is constant and equal to the value of the external reaction. So on the left-hand side, minus value equal to 27 over 24. And on the right-hand side, plus value, which is equal to 39 over 24, okay? In this case, the positive convention for the shear action is the one in which a piece of our beam is rotating in clockwise way. For the horizontal beam, there is an uniformly distributed load on the beam. And so what I expect is that the shear will vary linearly, okay, from the value of 7 over 6, which is the value on the left-hand side, until the value of 11 over 6, which is the value on the right-hand side, okay? On the left-hand side, the sign is plus. On the right-hand side, the sign is minus. So very easy computation to do if you know before which is the law of variation of the different quantities. Before moving to bending moment, let's see what we expect in terms of bending moment for the two columns. First of all, we expect that bending moment corresponding to the hinges, it's equal to 0. Afterwards, when we are moving along the column and we are making cut at an increasing distance from the ground hinge, the distance of this force from this cut is increasing. And so what we expect is a linearly increasing value of the bending moment, where the fiber in tension are the external fibers on the left-hand side, and again, the external fiber also on the right-hand side. Okay? For the horizontal beam, we have the shear, which is linear, and so we expect a parabolic variation of the bending moment. A parabolic variation of the bending moment with a 0 corresponding to the mid-hinge, okay? And there is also a maximum or a minimum value where the shear force, the shear internal force, is a zero value. So let's look at the bending moment diagram. As I anticipated in the left-hand side column, we have a linear variation of the bending moment, and of course, the fiber in tension are the one on the external side, on the outer side. Similarly, we have a linear variation of the bending moment on the right-hand side. And of course, in order not to have a rotation of this angle, and also on this angle, so if in the column there is a bending moment whose value is 27/12, also on this side should be a bending moment whose value is equal exactly to the same. And the same happens on the right-hand side. Afterwards, what we have said? We have said that there is a zero value of the bending moment corresponding to the internal hinge, and there is a maximum value corresponding to the value, to the point, sorry. Why? What's happening? Okay. A zero value corresponding, maximum value of the bending moment corresponding to a zero value of the shear. Okay. Everything is quite easy. So let's move to the cross section. The first question, the case of the cross section, in the case I have assumed the value of alpha equal to 1. So the width of the upward plunge is 190 millimeters. Okay. In order to evaluate the moment at first yielding, since we know the yielding stress, which is equal to 235 Newton per square millimeter, okay? Since we know this, in order to evaluate the moment at first yielding, I need to evaluate the inertia bending moment with respect to the center of the beam, and from this value to evaluate the quantity we have denoted as WL, which is the inertia moment over half the height of the beam. So in order to evaluate the inertia moment, of course, we have to consider our cross-section as divided in three rectangles. Okay, the first rectangle is the web, thickness 5 millimeter, height 180 millimeter. So the inertia moment is thickness 5 times 108 cube over 12. Afterwards, I have to consider the effects of the two flanges. The two flanges are two rectangles, okay? The area of each rectangle is 10, the thickness times the width of the flange, 190. And we have to multiply the area of each flange, in fact there is a 2 here, by the distance of the center of the flange and the center of the overall cross-section, okay? Since the height of the overall cross-section is 200 millimeter and the thickness of the flange is 10 millimeter, this distance is 95. So times 95 square. In addition, we have to add the inertia bending moment of this rectangle with respect to an horizontal axis passing for eccentric. So 190, which is the base, times 10 cube over 12. And I obtain a certain value. Afterwards, this value should be divided by half the height of this beam in order to obtain WL. And in order to obtain WL, I have this value, okay? So 367,451.7 cube millimeter. At this point, in order to evaluate the first yielding bending moment, I have just to multiply this value times the yield strength, and afterward I will pass in kilonewton times meter, and the value of my in terms of kilonewton per meter is 86.35. Afterwards, I have just to evaluate the plastic bending moment. In order to evaluate the plastic bending moment, remember, I have to evaluate the plastic force F1 and multiply the plastic force F1 by this distance, 190. Afterwards, I have to evaluate also the plastic force F2 and multiply this force by this distance. Of course, the value of F1, if the value of the yielding stress times the area of the flange. The area of the flange is 109 times 10. While concerning the force F2, the force F2 again is the product of the yielding stress Fy times half the area of the web, okay? And half the area of the web is 90 times 5. Afterwards, it is very easy to evaluate the maximum bending moment, the fully plastic bending moment. And by making the ratio by MPL and My, I can easily evaluate either the value of the plastic ratio psi, that in this case is 1.09, around 1.09. And in addition, it is also easy to evaluate the value of the WPL. Okay, so the solution also of this exercise is quite easy. Okay, any questions about this before coming back to steel structures?
Dear Professor, this homework will be the one that will be evaluating for our final results.
No,
No.
no. The next one will be useful for evaluating your final results. The one I will give you at the end of my presentation of this morning. And you have basically 1 week to deliver the result to us. But I will explain after. But basically, when I ask him to you if there are questions, basically I expect some question on what I have shown to you. Okay, any question on the solution on this first homework or not? Okay, no question on this, and then let's move to another subject. Okay, I have already shown this to you because we are talking about the properties of steel structure, and we have seen that the property of steel structure are basically related to the chemical composition of the steel. All the possible performance of the material that we can define, such as the strength or the plastic deformability or ductility, the ultimate strain, the hardness, the resistance to corrosion, and the welding capacity are depending on small quantities characterizing the chemical composition of the beam, notwithstanding the fact that steel comes from an industrial production. We have already commented basically that in a steel structure we have three main types of geometrical imperfection. The first type are imperfection of the cross section. Of course, we have very small tolerances in terms of perpendicularity, in terms of symmetry, in terms of transversal straightness. So in order not to have visible effects on a cross section like the one I've shown in this slide. But there are not only imperfections at the level of the cross section, but there are also possible imperfection of the element of one column or one beam. What does means imperfection of the element? That the element is not perfectly straight, and if an element is not perfectly straight, the consequence of this is then when I apply an axial force like in this column or in the right hand side column, instead of having an initial value of the bending moment which is equal to 0, I have not an initial value of the bending moment which is equal to 0, because we have a bending moment which is related to the product of the applied vertical force times the initial imperfection delta. Okay? Of course, if we have imperfection at the level of the cross section, if we have imperfection at the level of the elements, basically it is possible to have also some imperfections at the level of the structural system. Imperfections that are coming by, for example, imperfect positioning of the connection. So 1 millimeter of error in the overall geometry, or few millimeter of mistakes in the overall geometry. So imperfection that are more or less related to the construction process. Another aspect to be very clear is that the constitutive law of the steel material. In order to obtain this kind of constitutive law, or sigma epsilon curve in the laboratory, generally we refer to simple tension test. The sample to be tested in the laboratory is something like this. So it is a central region of cylindrical cross-section with two, again, cylindrical end parts. Generally, the cylindrical end parts are the ones that are placed in the test machine, okay? Generally, what we measure in this kind of test is the axial force, okay, applied at both ends of the sample, and the variation in the length of the central part of the sample. We have already commented that generally from the force we can pass to the normal stress by dividing by the area of the cross section, by the area A0, and we can pass also to the normal deformation, to the normal strain, okay, to the normal strain by dividing the elongation by the original length. In fact, we know, I remember to you, that the engineering definition of strain is the variation of length of a fiber which was originally of unit length. Okay? If we put in diagram the force divided the area and the increasing in length divided the original length, we obtain the stress-strain relationship of the steel. And we have already commented that there is a first part which is completely linear. It is a linear elastic behavior. It means that when I'm reaching point P by increasing the load, if I'm going to decrease the load, I will follow exactly the loading path in the unloading. Afterwards, we have a non-linear elastic behavior. So you see that the behavior between P and E, it's non-linear, but it is still elastic, like in a rubber. This means that when I have reached in loading point E, it is possible to, in the unloading, to reach again the point 0, the point O, the origin, by following the same loading path. Afterwards, we have another path, ES, which is the beginning of an elastic behavior. If we are reaching an intermediate point between E and S, the unloading path is different from the loading path. And so we will have an unloading path that will be parallel to the straight line OP. After point S, we have the yielding, okay? And again, between S and S prime, the behavior is inelastic. So the unloading follows a path which is not equal to the original one, but it is parallel to the elastic path OP. This means that if I'm going to point S prime and then I want to unload, I will have a residual strain corresponding to zero stress. So, like in the case of a fork, when you do this, so you have, after the force has been removed, a residual strain, which is very apparent. This happens because we are in the unelastic range of behavior of steel. After the point S prime, we have a strongly unelastic behavior with a first path in which the strain and the stress are increasing. This path is called hardening path. In Italian, incrudimento positivo. After the maximum value of the stress, we have a softening part. So in order to make the strain increase, we have to decrease the stress. And this is the softening part of the behavior. In Italian, softening is incrudimento negativo. Okay, so this is the behavior of steel, of a real sample of steel. Generally, we approximate the behavior of the material as an elastic, ideally plastic behavior, as we have already observed. Of course, there are some parameters characterizing the behavior of the steel. For example, the density of the steel is 7,850 kilonewton per cube meter. The Poisson coefficient is equal to 0.3. The modulus of elasticity is 210,000 Newton per square millimeter. Similar, the shear modulus can be obtained from E and Ni by using this classical formula for elasticity. So it's the ratio between the Young's modulus, or the modulus of elasticity, over 2 times 1 plus Ni. In addition, the value of the coefficient of thermal expansion is equal to 12 times 10 minus 6 degrees centigrade at minus 1. So it means that for each value of thermal variation of 1 degree centigrade, we have an increase in the length of a sample, which is equal to this number, okay? Of course, it is possible to characterize the strength of a steel in terms of yield strength and ultimate strength. These tables are written in Italian, and also these characteristics of the materials are not the last one, but what I would like to underline is that in terms of yield stress, the commercial steel belongs to three main classes. For the first one, we have the steel strength of 235 Newton per square millimeter. For the second one, we have 275 Newton per square millimeter, and for the third one, we have 355 Newton per square millimeter. Nowadays, these types of steel are denoted as S235, S275, S355. Okay? So when we are dealing with a steel cross-section, this is the classical terminology that we use. So this part is the web and the outer part are the flanges, okay? So we have several type of beams. So the W shape or white with flat flanges, the C shape or channel cross section, the S shape like I-beam or standard I-beam, and so on. And I can show you various kind of industrial production. For example, this is typical steel for reinforced concrete. This is instead pictures of typical production of I-beams or universal beams that are still kind of I-beams. Against, for example, we have C-shaped beams or channels or round bar. Round bar might be with a cross section like this, but also with different type of cross section. Afterwards, it is possible to have in the industrial production the rails or cross section. We are very similar to the one used in rails in railways. The other kind are flat bar like this, okay? In other types, there are the steel type, the steel pipe in rounded cross section or also in square tubing, something like this. So we can see that the industrial production is includes a huge number of products, like, for example, the stranded for ropes and cables in cable stayed bridges or in prestressed concrete cables. Afterwards, there are the reinforced welded steel mesh that are elements welded like this, including bars of quite small diameters, okay? And afterwards, finally, we have, of course, the bolt and the head bolts, okay? Which generally are made in coated or galvanized steel. Okay, so again, we have the hexagon nut, other time of hexagon head screw, and this is a very quick summary of the possible industrial production of steel. As I anticipated before, at present, the kind of industrial steel are denoted as S235, S275, S355, also S450. And of course, the number after the S is just the value of the yielding stress of the characteristic yielding stress. We have also to remember another aspect, that this kind of value of the yielding characteristic stress also for normal thickness of steel, so thickness that is lower than or equal to 40 millimeter. When the thickness is larger than 40 millimeter, is in the interval between 40 and 80 millimeter, we have to correct a little bit the maximum, the value of the yield stress, and for large thickness elements, the value of the yield stress is a little bit lower than the one of normal thickness elements. We have seen that in the practice, generally we refer to an elastic, ideally plastic behavior of the steel. So elastic and linear until the yielding value of the stress, and afterwards we have a constant value of the stress. And I have already presented to you basically the behavior of a cross section according to this kind of behavior. Okay, any question on this very quick summary? I would like to stop sharing just for a while. Okay, there is something out the room. Now I admitted him. Okay, so question on this part or not? If there are no question, okay, we have to share again. Everything is okay? Do you see the slide? Please, quick answer. Okay, perfect. If you remember, during last lecture, I have already introduced the classification of the steel cross-section. Okay, and we have seen basically that this kind of classification is ruled by the possibility of having a local buckling. Okay, so for example, we have already commented about the class 1 cross-section. Class 1 cross-section are those which can form a plastic hinge with the rotation capacity required from plastic analysis without any reduction of the resistance. So the class 1 cross-section are the ones for which it's possible to obtaining the fully plastic bending moment, and we have also a full capacity of rotation. Okay, for a cross section like this, we can use the strength verification either in terms of moment of shielding or in terms of fully plastic bending moment, and so we can use the both type of MN interaction curve. Also, for class 2 cross-section, is possible to refer to both the MN interaction domains, because class 2 cross-section are defined as those which can develop their plastic moment resistance, so the fully plastic bending moment, but have a limited rotation capacity because local buckling is beginning to play some role. Of course, when passing to class 3, it is not possible to develop the fully plastic resistance because of local buckling of the compressed part of the cross-section. So for a class 3 and even for a class 4 cross-section, we have to use an elastic strength verification. Indeed, we have also to remember that for class 4 cross-section, we have local buckling before the attainment of yield stress in one or more part of the cross section. So in this case, maybe it's better to protect the yielding bending moment, for example, by using some quite large safety coefficient. But since local buckling and overall buckling is so important in steel structures, I would like to remember something about the possibility of local and global buckling. Maybe we are more accustomed to talk in terms of overall buckling or stability. So generally, when we have a compressed beam, if the load is perfectly centered, okay, and we have already seen that this is not always the case in the real industrial production due to the imperfection of elements. But let us neglect in this moment the possibility of the imperfection at the elements level. Let us refer, for example, to a perfectly vertical column with applied an axial load. Okay? In a case like this, we know that there are no transversal deflection. If we want to apply a transversal deflection, I have to push a little bit against my vertical column. And what I expect in the practice that after my push ends, I will recover exactly the vertical configuration, the ideal vertical configuration. But this is not the case when buckling, global buckling occurs, because we have global buckling in case a small push can generate a very large displacement, and the displacement is not recovered after the small push ends. Of course, there is also the possibility of having some kind of local phenomenon. So some local buckling in our steel elements due to some kind of local instability. When we talk about of instability or we talk about buckling, the idea is a small action generates a very large effect. When in every kind of phenomenon, physical, mechanical, and even numerical, something like this happens, we can talk of instability. Of course, the simplest way of defining stability or instability is to look at a small ball which is constrained to something, a guide like this. Of course, we can define three different equilibrium positions. The first one is the equilibrium position in which our ball is in the bottom part of the guide. Second case is when we have an equilibrium with our ball that belongs to an horizontal part of the guide. And the third case is that now we have that our ball is on the peak of our guide. Of course, if we look just at the equilibrium equations, all the three cases are very similar, because the reaction of the guide is vertical and is opposite to the weight of the ball. Okay, so vertical and opposite to the weight of the ball in the first case, vertical and opposite to the weight of the ball in the second case, weight vertical and opposite to the weight of the ball in the third case. But of course, it's obvious that the three cases are very different, and we can understand the difference by applying a small perturbation. When I apply a small perturbation in the first case, I clearly understand that when the perturbation ends, the initial equilibrium position is completely recovered. Okay? So in this case, the equilibrium position is said as stable. In the second case, the situation is different, because if I apply a small perturbation, the final configuration after the small perturbation ends is different from the original one, but it is very close to the original one. So in this case, we can talk of a neutral equilibrium. The third case is the unstable case of equilibrium, because we can clearly understand that a small perturbation applied to the ball in the peak of our Mountie generally induce a new configuration equilibrium, which is very far from the original one. And so a small action induces a very large effect. And this is the definition of instability. Now let's move, for example, to another kind of case in which the mechanical system is again not a real one, is an idealized one, because we can refer, for example, to an indefinitely stiff vertical beams which is hinged at one end and connected to a spring at the other end. And let us assume, for example, that this kind of structure is subject to the action of a force in tension, okay? And let's apply a small perturbation. A small perturbation means I move of a small angle theta this beam from its vertical equilibrium position. What happens? Of course, the springs undergoes an elongation, and so due to this kind of elongation, there is a force opposing this elongation. So I have a force here applied to this end of the beams, and this force, of course, is directed in this direction, okay? So after I have moved my equilibrium position and of an angle theta, and I can observe the bending moments with respect to the hinge connected to the ground. I observe that there is an anti-clockwise bending moment associated to the force P, and again also an anti-clockwise bending moment associated to the force, to the reaction in the spring. So there are two forces, and both of the two forces are anti-clockwise. So what happens is that this element, after the perturbation stop, is moved again in the vertical original condition. So basically, we have to assume that when the action P is a tension action, generally this structure, this very simple mechanical system, is always in a stable kind of equilibrium. Okay, now let's do something different by changing the direction of the vertical force. Now the vertical force is in compression, and I will apply a small perturbation by introducing a small angle of theta. Again, I have an elongation of the spring. And so again, I have a force in the spring, and if we are in the small displacement field, I can say that its elongation is equal to theta L, and so the force in the spring is K times theta L. But now, if we look at the moments with respect to the hinge at the ground, we can observe that the compression force generates a moment which is destabilizing because it is clockwise, and the effect of this moment is moving our beam far from its original equilibrium position. On the other side, the force in the spring is a stabilizing force, in the sense that the corresponding moment tends to move back our beam or our column to the original equilibrium position. And the moment is anti-clockwise. So now we have a stabilizing action and a destabilizing action. If the stabilizing action is dominant, the equilibrium is stable. If the destabilizing action is dominant, then we can say that the equilibrium is unstable. Because if the destabilizing force is dominant, we will have a new equilibrium position which is very far from the original one. Of course, when we have that the stabilizing moment is exactly equal to the destabilizing moment, and the stabilizing moment is K times theta L times L, whereas the destabilizing bending moment is P times this displacement, and this displacement is theta L. When the two are equal, we have a neutral condition of equilibrium. A neutral condition of equilibrium means that there is the possibility of a new equilibrium condition which is different from the original vertical one, but it is quite close to this. When the force P is lower than KL, then we have that the stabilizing force is dominant. So we have a stable kind of equilibrium. Otherwise, when P is larger than KL, it's the destabilizing moment which is dominant, and so we have an unstable equilibrium. We can observe that exactly the same happens in the case of a real beam. A real beam or a real column is different from an ideal one because the deformability is distributed along the beam or along the column. And so we saw that we know that for an ideal column, for example, that is constrained at both ends by 2 hinges, we have a value of the critical load, and the critical loads or Eulero load is the one corresponding to the neutral equilibrium. The value of the critical load is equal to Greek P square times the Young's modulus times the inertia moment of the cross section over L0 square. L0 in the case of the column which is connected with the hinges at both ends, it's equal to the length of the beam. Otherwise, if we are going to consider different constraint condition at the ends of the column, L0 is denoted as effective length, and it is generally a coefficient beta multiplied the real length of the beam. In the practice, the effective length is the wavelength of the deformed shape under the critical load. The deformed shape under the critical load, in this case of the Euler beam, hinge and both ends, the wavelength is of course equal to the real length of the column. But when we refer, for example, to a column in which there is a fixed end and a free end, of course, the deformed shape of the under the critical load is something like this. If we reflected this deformed shape with refer to the fixed end, we obtain a double wavelength. And so in this case, the wavelength L0 is not equal to the real length of the column, but it is equal to 2 times the length of the column. In this case, fixed end and hinge. This is the deformed shape corresponding to the critical load, and we can see that the wavelength of the deformed shape is, in this case, 0.07 L. In case we have, for example, a fixed end and another end in which it is not possible to have rotation, then the wavelength of the deformed shape under the critical load is equal, as we can see, as 0.5 L. Okay, and so generally, when we are dealing with the Euler beam, we can say that the critical load is Greek P square times E times J over L square. In the general case of a column with different constraint condition at both ends of the column, we can substitute L with the effective length at L0. Of course, since in a real cross-section we have 2 main planes of behavior of the cross-section, of course we have 2 different values of the critical loads in the XX plane of the cross-section and also in the YY plane of the cross-section. Okay, now this what I have shown to you so far holds for an ideal columns without imperfection whose behavior is indefinitely elastic. But we have recalled that a real industrial column is different from a real column due to the imperfections. So for an ideal column like this, no imperfection in the beginning, I have that the curve, the diagram in which we have on the horizontal axis the transverse deformation and on the vertical axis the load, is something quite easy, because if there is no initial deformation delta, when I'm going to increase the value of the axial load until I do not reach the value of the critical load, I have no deflection. Afterwards, there is the possibility of having a deflection which is not defined in value. Okay, so something like this: vertical until the value of the critical load, and afterwards there is an increase in the deflection without any increase of the applied load. Okay? But when we are in this position, okay, in this condition, there is an initial imperfection delta zero. And so what happens is that corresponding to a value of the axial load that is equal to zero, we have an initial deformation delta zero, okay? When I apply a small vertical load, of course, there is an increase in moment, and so there is an increase in transversal deflection. And so I will have an asymptotic curve like this that, depending on the type of the cross-section, might be followed until a certain value. If I want to express this value in terms of equation, I can see that the deflection delta corresponding to an initial imperfection of delta zero and a certain value of the actual load of the applied load P, of course, depends also on the value of the critical load. And so it can be expressed as delta zero times 1 over 1 minus P over the critical load. But of course, I'm referring now to an industrial column, but to an ideal elastic behavior. But we know that the real behavior of the material is not entirely elastic or indefinitely elastic. It is elastic plastic. And so at a certain point, there is a difference between the ideal curve, even if there is an initial value delta zero, and the curve corresponding to a real material, real elastic plastic material, to not only a real column with imperfection, but also a real column made in real steel. And the real steel is not indefinitely elastic, but of course is elastic, ideally plastic. Now, I would like to go back to the value of the critical loads and divide it by the area in order to obtain from the critical load the critical value of the normal stress. It is very easy, basically, because we know that the critical load is Greek P times E times J over the effective length L0 square. If I want to divide by A the area of the cross-section, I have just to put A here. Okay, I would like to rewrite this value of the critical stress. Okay, so it's equal to Greek P times the Young's modulus times the ratio between iota and A, and the ratio 1 over L0 square. Okay, let's look at the ratio iota over A. The ratio iota over A only depends on the transversal cross-section of our column, because iota is the inertia moment and A is the area of the cross-section. So in the standard tables of the cross-section, you can find both the value. So the ratio between iota and A entirely express the effect of the cross-section. Because, for example, we can have cross-section which are characterized by the same area, but by very different value of the inertia moment. For example, if we refer to a certain value of area and we try to concentrate a lot of area far from the center, the inertia moment is increasing, of course. And so also the ratio between iota and A is increasing. And this number, I repeat, this number basically expresses the effect of the cross section. This number is the square of a length. In fact, the inertia moment is measured as a length up to 4, whereas the area is expressed as a length squared. So the ratio between iota and A is generally denoted as I square. I is called radius of inertia. So when I express this in terms of the radius of inertia, I can have the ratio between I square and L0 square. L0 or L0 square is the effective length or the square of the effective length. Of course, it depends on the length of the beam or of the column and on the constraint condition. So it depends only on the transversal characteristic of our columns. So this ratio I square of L0 square is made by two terms. The first one, the one on denominator, basically depends only on the transverse cross section. The second one, the one on the denominator, depends only on the transverse, on what happens transversally in our columns, okay? And so from the knowledge of the cross section, from the knowledge of the length and of the effective length, so including also the constraint condition, I can obtain this number. Generally, this number is denoted as slenderness. The slenderness indeed is the ratio between the effective length and the inertia radius. And the slenderness depends only on the geometry of the structure, because L0 depends on the transversal, the geometry, and on the constraint condition. The inertia radius depends only on the characteristic of the transverse cross-section of our column, okay? So generally, I can express the critical stress in terms of Greek p squared times E, which are constants for a steel material, because Greek p is a universal constant, 3.14, and so on, okay? And E depends on the material. So for a steel, we know that the value of the Young modulus is constant. Lambda, the slenderness, depends only on the geometry, transversal geometry over geometry of the cross-section. If we put in one plane sigma and lambda, we obtain a curve like this. But of course, this kind of evaluation holds in the case of indefinitely elastic material, okay? But we know that real columns are made with imperfection and are made also on of a real steel. So a first cut in this ideal curve is due to the fact that the value of the critical stress does not exceed, cannot exceed the yielding stress. So we have a first cut here corresponding to the yielding stress. Of course, it is possible to define corresponding to the yielding stress Fy a value of slenderness of proportionality. The slenderness lambda p, which is equal, or it is called slenderness of proportionality, it's equal to Greek p times the square root of Young's modulus over Fy. Please do not ask how it is possible to evaluate this, because of course this can be evaluated by putting the critical sigma equal to Fy and then obtaining the value of lambda from Fy equal to Greek p squared times E over lambda square. It is interesting to observe that corresponding to the slenderness of proportionality, at the same time, we will have the value of the yielding stress, but also the beginning of an instability phenomenon. When the slenderness of the column is larger than the slenderness of proportionality, we know that we need to make a stability verification. When the value of the slenderness is lower than the slenderness of proportionality, we know that it is possible to perform a strength verification. And of course, the two kinds of verification, strength verification and stability verification, are different, because on one side I have to verify that the actual value of the stress does not exceed the yielding stress. On the other side, I have to verify that the actual value of the stress does not exceed the critical value of the stress, the value for which we have instability. Okay? Another aspect is related, another kind of reduction of this shape of our stability curve is related to the fact that this kind of stability curve has been evaluated for an ideally elastic behavior, while in the case of a real material, there is the effect of imperfection and there is also the effect of plasticity. So the real plasticity, the real stability curve is lower than the ideal stability curve. Something like this, okay? And so, of course, it is possible to redraw this kind of curve, not exactly in a plane sigma lambda, but in a plane, for example, sigma over critical sigma, or sigma over the yielding stress, and lambda over the proportionality value of lambda. If we do this, we can obtain different value of the stability curve. So the shape of the curve is exactly the same as before. Now, here we have not the value of the critical stress, but the value of the critical stress over the yielding stress. And on the x-axis, we have not the slenderness, but the slenderness over the slenderness of proportionality, okay? And so we can see that we have 4 different types of stability curve, okay? the different type of stability curve. Indeed, at present, there are 5 different curves of stability curve, because the curves called A is divided in A and A0. So we can also talk in terms of sigma ratio between the actual axial force over the area of cross section, and when we have to verify the stability, we have to check that this value obtained by our computation should be less than chi, which is function of lambda, because the critical load is basically function only on lambda, times the value of the yield stress over a coefficient of safety. So let's go back to the ideal curve. Let us assume that we know that our column, for example, is made in a column HEA, in I-beam HEA 300, okay? And it is 4 meters long. Since I know the length of the beam and how the beam is constrained, it is possible to evaluate the effective length L0. I know also the cross section. I have said that cross section is an HEA 300. So it is possible to evaluate the inertial moment and the area. And so it is possible to obtain the radius of inertia. So it is possible to obtain lambda. If I know lambda, and I suppose the lambda is this one, I can obtain the value of the critical stress. And then I have to compare the value of this critical stress protected by a safety coefficient with the actual stress. And this is done in this curve and in this equation, okay? Here you can have the coefficient chi, and here you can have the ratio between the yield stress and the safety coefficient. Generally, the different kind of curve, sorry, I had to rotate this kind of classification, can obtain from Eurocodes or from Italian standard codes, okay? And so we know which is the right curve, the right stability curve to look at. Okay, if we want to look at the stability curve, I will send you the tables of the stability curves, okay? So these tables, in this case, are related to the curve A, to the value of the yielding stress of 235 Newton per square millimeter. The value of the safety coefficient is gamma M1 equal to 1.05. And let us understand how this table works. So this table are given in terms of the slenderness. Okay, so for example, I would like to have a number from the audience. So please give me a number. I'm waiting. So I see 70, 80. No, I will choose the number. For example, 85. Okay. Good. Let's look. 85 is the value of the slenderness. As I said before, since I know which is the length at the constraint condition of my column, I can obtain from this the value of L0, of the effective length. I know the cross section, and so I can also obtain the value of the radius of inertia. Let us assume that the ratio between L0 and I is equal to 85. Okay, so lambda equals 0, 10, 20, 80. Okay, so this is 80, 81, 82, 83, 84, 85. So the value of the critical stress corresponding to a slenderness of 85 is 163.5 Newton per square millimeter. Okay, if I change the slenderness, because for example, I would like to change the length of my column, okay, and I, for example, assume that the slenderness is quite low, for example, something like very low, okay, 5 of slenderness. Corresponding to 5 of slenderness, I have 223.8. And you see that 223.8 is the value until I have a slenderness of 18. Okay, so for very low slenderness, as we expect, we have a value of the key coefficient, which is basically equal to F epsilon over gamma M1, okay? Because in that curve, I have this product, okay? When I'm going to increase, for example, to 85, the value of the slenderness, what it happens is that the critical loads becomes to begin very effective. For example, let's look at a quite high value of the slenderness. For example, 176. Okay, 176 is this number. So the critical load now is 56.2 Newton per square millimeter. The steel is again the same. So the yielding stress of the steel is 235, but I can obtain a critical load that is lower than 1/4 the maximum yielding value of the stress, because it is equal to 56.2. Of course, we can very easily obtain this kind of curves. Of course, the opposite of key is generally called in the international literature, it is generally called as omega, and omega is function of lambda. If you look at this, you can easily evaluate that the value of key is basically the ratio between the critical load and the value of F epsilon. Conversely, if omega is the opposite of key, omega will be F epsilon over the value of the critical load. So when I'm going to talk about buckling, in the elastic range, we have said that when we are on the side of tension forces, we can use the value of the stability equation, which is n over m epsilon plus m over m epsilon less than or equal to 1. When we have that n is in compression, it is obvious that we have used a different value for the stability check. In this case, it's better to amplify n by omega, and omega, we have said it's equal to 1 over key. Remember, key is the stability curve, so is the ratio between the critical sigma and the F epsilon, okay? and afterward we have to sum up this to an equivalent bending moment over my over times 1 minus p over critical p. The equivalent value of the bending moment might be defined in two ways. For example, it might be assumed as the maximum bending moment in the column. And this is a quite conservative assumption. Otherwise, we can define the equivalent value of the bending moment as a value in which the diagram of the bending moment along the beam or along the column has the same area of the actual diagram of the bending moment. Okay, now I would like to finish, but before doing this, I would like to ask you if there are any question of this aspect. I would like to finish my part of presentation by assigning you the homework for next time, and this time this homework is part of your evaluation. So, question on what I have shown about buckling of steel members under compression. Questions?
Professor, can you please explain the exact relationship between omega and lambda?
Yes. Okay. You have understood that this is lambda, okay?
Yes.
So if you know how your column is made, you can obtain the value of lambda as the ratio between the effective length and I, okay? That's clear. So you know the column, now you know the value of lambda, okay? How it is possible to define the stability curve? Okay, we can define the stability curve both in terms of chi or both in terms of omega. Okay, so look at this. Here you have the reduction factor. Okay, in order that we have that the current value of sigma, okay, equal to P over A should be equal to the critical load over gamma M1, okay? Because this is the meaning of the stability curve, okay?
Yes.
I don't know if you understand this passage.
Yes, just what is gamma M1?
Okay. Key in this equation is the critical sigma, okay, over Fy. In order that critical sigma over Fy, it is possible to simplify this value of Fy with the value of Fy here in key, okay? In addition, when I'm doing this, this relationship is P over A less than or equal to critical sigma over the safety coefficient gamma M1, okay? Instead of defining chi, which is only depends on lambda, okay, as the ratio between the critical stress and Fy, I can define omega as the ratio between Fy and the critical stress, in order that in the case we are referring to chi, chi is always lower than 1. In case we are referring to omega, omega is always larger than 1, because in case we refer to chi refers basically is a reduction factor to applied to the strength Fy. Instead, if I'm going to use omega, omega is an amplification factor applied to the load. In fact, look at this. In this case, omega is multiplied by the axial load. So omega and chi are exactly the same concept, because one is the opposite of the other. Okay, chi is sigma critical over Fy, omega is Fy over sigma critical. When I use chi, I'm using chi in order to decrease the value of the strength. When I'm using omega as an amplification factor to the value of the axial force. More clear?
Yes, thank you so much.
Okay. Any other questions? Okay, no other question. Let's come to the homework. This homework. Sorry. This homework is divided in 3 parts and is part of the final examination. We have a structure which is quite similar to the one I have solved for you at the beginning of my lecture. So it's an arch with 3 hinges. It is subjected only to a vertical distributed load on the horizontal beam, and the difference between the different structure is for the height of this column. The height of the column is beta L, and beta is 1 plus alpha over 5. So if your name is Anna, for example, the first letter is 1, and so you have 1.2 L. If your first name begins with U, then you have that alpha is equal to 5, and then you have beta equal to 2, and so we have 2 times L. Of course, you have to compute the external reaction, the diagrams of intensity, and the diagrams of internal action, N, T, and M. Afterwards, I have defined a C-shaped channels cross-section, and with reference to this kind of channels cross-section, I would like to ask you to please find the coordinates of the center of the cross-section, okay? And afterwards, I would like to ask to you the inertia moment with respect to the horizontal and vertical axis passing from the center, for the center of the cross-section. In this case, the difference between the different exercises is again in terms of this coefficient alpha, which is ruling the height of this channel, okay? Finally, I have an I-beam. Again, the difference between the various I-beam is in terms of this coefficient alpha, and again, alpha corresponds to the first letter of your first name. Again, the structure is made in a steel S235, and I would like to ask you to find the first yielding moment, MY, the full plastic bending moment, WL and WPL, and the ratio psi. Of course, you are asked to solve this homework by October 23, okay? And to send the solution both to myself, carmelo.gentile@polimi.it, and to Antonello Ruccolo, okay? antonello.ruccolo.polimi.it. please don't be lazy. We kindly ask to you to generate your homework in a PDF file and to send us the PDF file. The name of the PDF file is like this. ST01 is common for all. Underscore your last name, underscore your first name .pdf. For example, if I have a student named Roger Federer, the file is sd01 underscore Federer underscore Roger.pdf. Is everything clear? Please send the worked homework in time, because we cannot consider, as you can easily understand, homework that are received out of time. Please. Of course, please do not send message to myself and Dr. Ruccolo in order to ask clarification on this exercise. If you need clarification on this exercises, this is the time for asking to us. Okay? Is everything clear? Okay.
I'm sorry, could you repeat the second exercise?
Do you see the cross section? I will send you this these slides after the end. Do you see the cross section?
Yes.
So you have to find the coordinate of the center of the cross section. I suppose that the center of the cross section is more or less in this position. Something around this position. And afterwards, once you have evaluate the position of the center of the cross section, horizontal axis, vertical axis, passing for the center, and please compute the inertia moment with respect to horizontal and vertical axis passing for the center of the cross section. Okay?
Yes, thank you.
Any other questions? So, if this is not the case, now it's time to stop recording.